Welcome all of you. We are in the process of solving a numerical problem on synchronous machine. Here we will be solving a numerical problem on three-phase star connected alternator. So as you can read over in the problem, we have been given a three-phase star connected alternator with synchronous impedance of 0 plus J5 ohm per phase and is connected to an 11 kilovolt system. The alternator power output is found to be 10 megawatt and reactive power output as 3 mvar. Mvar means megavolt ampere reactive. So we have to compute the magnitude of excitation voltage, load angle, line current and power factor. So first of all, I would recommend that you just notice these things which I am underlining with red ink. First of all, I am underlining this particular line which is saying synchronous impedance. So synchronous impedance, why I am underlining it, why I am making an underline on this sentence or on this phrase synchronous impedance, I will let you know shortly. Second one is that it is written that reactive power output as 3 mvar. So I will now focus on these 2 points. So number one is that synchronous impedance. So synchronous impedance, this particular phrase gives an indication that this implies that it is a round rotor alternator. It is a round rotor alternator. So the synchronous machine is a round rotor alternator. Round rotor alternator. So it is round rotor. How do we know? Because the word synchronous impedance is there. Had it been salient pole type synchronous machine, let me write in another ink. Had the synchronous machine, had the machine being salient pole type, in that case the word direct axis synchronous impedance, direct axis synchronous impedance and quadrature axis synchronous impedance would have been given, would have been provided in the numerical problem. So these points will not be that much of difficulty for you, because these are going to actually help you understand the problem. So I have tried to indicate this particular point, that the word synchronous impedance implies that it is a round rotor alternator. Had the machine being salient pole type, in that case the word direct axis synchronous impedance and quadrature axis synchronous impedance would have been provided in the numerical problem. Now what was my second line which I have underlined? I would say you look out very carefully. It is written reactive power output. So let me write it over here. It is written in the problem reactive power output. So reactive power output, what it implies? that alternator is delivering reactive power. So it is a vital piece of information. We are saying that alternator is delivering reactive power, isn't it? So let me write that. This implies that alternator is delivering alternator is delivering reactive power output, delivering reactive power output. So the word reactive power output, this particular word output, this is very important thing. I would like you to notice it. The word output is mentioned. So output thing, this implies that alternator is delivering reactive power output. So this also implies that the alternator is overexcited. This implies that alternator is overexcited. Alternator is overexcited. Alternator is overexcited. Let me write it neatly. Excited. So how do you know alternator is overexcited? This is because an alternator delivers. Now the word alternator can also be replaced by synchronous generator. So synchronous generator and alternator both are synonyms. You can use them synonymously, one for the other. So what I am saying, this is because I mean to say alternator is overexcited. This is because an alternator is capable of delivering reactive power, is capable of delivering reactive power, is capable of delivering reactive power when it is overexcited. So an alternator is capable of delivering reactive power when it is overexcited. So I have not started solving the problem right now, but these points are very much vital, because you know that for solving a numerical problem, the first thing is that you should be able to understand, and also you should derive or extract some of the meaning which may not be explicitly mentioned in the problem. Rather, you have to fish out the meaning by reading the statement of the problem. So that is what I have done here by writing 1 and 2 and underlining the points. You can see the word synchronous impedance. This thing implies that it is a round rotor alternator or cylindrical rotor alternator, because had it been a salient pole type, in that case there would have been two reactances provided. I mean to say there would have been two synchronous reactances provided, namely direct axis synchronous reactance and quadrature axis synchronous reactance. That means XD and XQ. And the second point is that it is mentioned in the problem that reactive power output. So the word output signifies that alternator is delivering reactive power. Now when an alternator is going to deliver reactive power, this is only possible if the alternator is overexcited, because when an alternator is overexcited, it is capable of delivering reactive power. So these two important things we have found out. Now what is our next step? Next step will be, let me add a page over here. So what I am going to now say that since alternator is overexcited, so operating power has to be lagging. So I have to also make out this meaning that when an alternator is overexcited, let me write it. When an alternator when an alternator is overexcited, then it operates at lagging power factor. Then it operates at lagging power factor. Lagging power factor. Now, when it is overexcited, it is going to operate at lagging power factor. This we are saying for alternator, but I need to mention here that the alternator in discussion above is synchronized with the grid, is in sync. Let me use some another phrase. The alternator in discussion above, it is assumed to be synchronized with grid, synchronized with. Now there are different words used. Some people can say the word grid, synchronized with the grid. Even some people can use the word infinite bus. So this can be also written as infinite bus. Now infinite bus is a bus whose RMS value and frequency remains constant, regardless of the fact whether you are drawing power or adding power to the grid or the infinite bus. The voltage and frequency will remain always fixed and constant. Now, this particular statement that when an alternator is overexcited, then it operates at lagging power factor. This we have said for this alternator, which is synchronized with the infinite bus or grid. Now, let us solve the problem. So, we have seen that by the problem statement, it can be extracted that number one, that it is a round rotor or cylindrical rotor alternator because the synchronous impedance is given, and number two is that it is delivering reactive power output. That means what? It is overexcited, and when an alternator which is connected with the grid is in overexcited condition, it operates at lagging power factor. So by taking that thing into consideration, according to the problem statement only we have derived it, we will draw the phasor diagram of an alternator which is connected with the grid, and of course it is operating at lagging power factor. So we will start with the terminal voltage Vt for the alternator. Here terminal voltage Vt, let us say it is the per phase voltage, per phase. So this is our terminal voltage Vt. So this is our reference phasor. Now with respect to terminal voltage Vt, the armature current Ia is going to lag because we have said it's a lagging power factor. The alternator is operating at lagging power factor. So the armature current of the synchronous generator or the alternator is lagging the terminal voltage Vt by angle theta. So this is your power factor angle theta. Now what I am saying is that we have been provided the synchronous reactance but not the synchronous impedance. If you can look at the problem statement which I have shown on the screen right now, the synchronous impedance is given as 0 plus J5. 0 plus J5. So 0 stands for resistance part, that is the real part. So that is 0. So armature resistance is not provided, it is shown as 0. So we will not take the armature resistance into consideration. We will only take the synchronous reactance into consideration. That is, synchronous reactance is denoted by symbol X suffix S. Synchronous reactance is denoted by symbol X, and in the suffix we write S to denote that it is synchronous reactance. So XS. So we will say that the reactive voltage drop. So let me indicate this over here up to this point. Now reactive voltage drop will be in quadrature with the armature current. Reactive voltage drop will be in quadrature with the armature current. So I am going to draw that only, reactive voltage drop in quadrature with the armature current. So which one is your reactive voltage drop? I will indicate on the diagram. Be with me. So this particular thing is your J multiplied by IA means armature current per phase, into XS. XS means your synchronous reactance. So sum of this phasor sum of Vt and the voltage drop in the synchronous reactance will give us the excitation EMF, that is EF. So excitation EMF EF is this one. Now in this phasor diagram, by default all the quantities are per phase quantity. All the quantities are per phase quantity. So this is your EF. Now the angle between Vt and EF is denoted by delta. Delta is known as your load angle. So delta is known as the load angle. So delta over here is known as load angle. Delta is known as load angle. Delta is known as load angle. Theta is known as power factor angle. Theta is known as power factor angle. And the angle between EF and IA, although we need not calculate here, but I am still showing the angle between EF and IA. This particular angle is denoted as psi, where psi is your known as internal power factor angle. It is known as internal power factor angle. Internal power factor angle. Now after having drawn the phasor diagram of the alternator synchronized with the grid and operating at lagging power factor because it is overexcited, we can now write something based on this equation. So let me do one thing. Let me name these things so that it will be easier for us to identify. So let us say this is your point O, this is a point A, this is your point B, this is your point C. So now we will write some equations which will be thought to be useful for us from the point of view of solving the numerical problem. So what is it we are going to write? We can see that from the diagram that OC equals to Vt cos theta. It is given by Vt cos theta, and AC is given by Vt sin theta. Vt sin theta. And obviously we can easily make out that AB is your the voltage drop in the synchronous reactance part, that is IA into XS. And what is EF? EF is your nothing but OB. Now we can do one thing, is that we can consider the right angle triangle OBC. So if I write like this, consider right angle triangle, consider right angle triangle OBC, then we can write OB square, that means the hypotenuse square, equals to the perpendicular square, that means AB plus AC whole square, plus the base, that means OC. So from this, it is not a difficult task for substituting the meanings of the line segment. Line segment OB means your excitation voltage per phase, that is EF. So this is your EF square. Now let me mention here what is EF. EF is your excitation voltage per phase. So EF is your excitation voltage per phase, excitation voltage per phase. And Vt is your terminal voltage per phase. Vt is your terminal voltage per phase. It is your terminal voltage per phase. This is your terminal voltage per phase. IA is your armature current per phase. So we can write it here somewhere. Let me write it over here. So IA stands for armature current per phase. IA stands for armature current per phase. Armature current per phase. Armature current per phase. This is your IA. Now EF square equals to, what is AB? IA into XS. IA into XS plus, what is AC? It is your VT sin theta. VT sin theta whole square plus, what is OC? VT cos theta. VT cos theta. VT cos theta square. That is your OC square. So now from this, it is not a difficult task to calculate EF. What will be EF? EF is your IA VT sin theta plus IA into XS, this whole square plus VT cos theta square. This is one thing we have got from the phasor diagram. Now let me introduce you to some other terms. So let me add a new page. Now all of know that from power triangle, this thing can be easily written. Power triangle I am drawing. It is a very known concept to all of you. You have done in your basic electrical. So from power triangle we can write like this. This is your apparent power. So this thing is your apparent power. This is given by your root 3 VL into IL, or you can also write 3 VT into IA. So let me make it more clear. This can be also written as 3 VT into IA. 3 VT into IA. Now what is this one? This one is your reactive power. This thing is your reactive power, and it is given by root 3 VL IL into sin theta, or this can be also written as 3 VT into IA into sin theta. Likewise, the base can be written as root 3. Let me write first what it is said as. This is known as active power. This is known as active power. So active power, this can be written as root 3 VL IL into cos theta, or you can also write this as 3 VT into IA into cos theta, where theta is the phase angle between phase voltage and phase current. That is your theta. So we should remember this, that here theta equals to time phase angle, or simply phase angle between phase voltage VT and phase current IA, and phase current IA. Now we can actually derive another equation for the active power delivered by a synchronous machine. Let me write this. So the active power delivered by a synchronous machine, let's say here alternator we are dealing with. So let me write the active power delivered by alternator by an alternator can be written also as can be also written as now when we are writing this, we are assuming that armature resistance is 0. So it is given in the problem already. So that's why we are trying to consider this case, assuming RA equals to 0. That means armature resistance equal to 0. So what is it? It is your 3 VT into EF, 3 VT into EF whole divided by synchronous reactance XS multiplied by sine of delta. So this is your active power delivered by an alternator. Active power delivered by an alternator. Active power delivered by an alternator. So we will also utilize this particular equation. So 3 VT into EF divided by XS. XS means your synchronous reactance. This whole thing multiplied by sine delta is your active power delivered by an alternator. So we will consider these two things, and we will now start solving the problem. So let me add another page once more. So we will now let me see if I can copy this or not. If I can copy it, it will be better. No, it's not getting copied. So I have to scroll down and up like that. Okay, we will do. So first of all, it is 3-phase star connected alternator. So we will write that 3-phase star connected alternator. So this is your this thing is your 3-phase star connected alternator. So 3-phase star connected alternator. 3-phase star connected alternator. This is given. What else is given? Another thing is that synchronous reactance XS is given as 5 ohm. Number one here is that line voltage is given as 11 kilovolt. It is written in the problem that it was mentioned in the problem that it is connected to a 11 kilovolt system. Now by default, if nothing is mentioned, the voltage has to be taken as line to line voltage. So since nothing was mentioned in the problem, so by default I will take that it is line to line voltage. So VL is given. Now how much was the active power delivered? It was 10 megawatt, and reactive power was 3 megavolt ampere reactive, that is mVar. Let me check it. 10 and 3 mVar. So it is 10 and 3 mVar. Now we have written all the data. Synchronous reactance is 5 ohm, reactive power delivered is 3 megavolt ampere reactive, and active power delivered is 10 megawatt. So now we will calculate the apparent power by using the power triangle, which I have shown just now some time ago. So you can easily now calculate the apparent power. So what is apparent power? Apparent power will be square root of 10 plus square of 3. It should be square root of 10 square plus 3 square. So this was your 3 mVar megavolt ampere reactive, and this was your 10 megawatt. This was your 10 megawatt. So 3 mVar, and this was your 10 megawatt. So from this you can find out the apparent power. So let us calculate the apparent power. So square of 10 is your 100 and this is your square of 3 is your 9. So 109 square root. So from here what you get, you are getting S. S means your apparent power. You are getting S. S equals to apparent power. This thing is your apparent power. This thing you are getting, and what we know that S can be also written as root 3 into VL into IL. So what is S here? S is here given by square of 10 plus square of 3. This will be in, mind you, this thing will be in mega volt ampere, MVA. And this is your root 3 into VL. VL is your 11 kilovolt multiplied by IL. So from here you will get line current in terms of your kiloampere. You will get line current in terms of kiloampere, isn't it? So let us now calculate this. Now for calculating this, let me use the online calculator. So with the online calculator we can calculate it. So let me calculate with the help of this online calculator. So now what will be our next step? Now you see from this equation it is sure that we can get the value of line current connection. Line current and phase current are same. So let me mention here for star connection IL to phase equals to IA. That means line used to phase current calculated. So once you calculate IA, you are calculating. So let us calculate square root of 10 square is 100 plus 9, 109. So 109, I have to take the square root of this. So it is 10.44, isn't it? 10.44 mega mvar, 10.44 MVA actually. So this thing is your 10.44 into 10 to the power 6. This thing divided by root 3 multiplied by 11 into 10 to the power 3. It was in kilovolt. So 10.44 by 11, let us do it. 10.44 by 11. So it will be like this, and then you have to again divide by square root of 3. So square root of 3 is 1.732. I am writing it that only directly, 1.732. So it is coming like this, 0.547. Now it is in kiloampere, so I can multiply by 1000. So it is coming as 547.99. So you can as good as take as 548. So this will be 547.99 ampere. So you can take as good as 548 ampere. So we have solved the one portion of the problem. We have been able to compute the line current or the phase current. Since it is a star connected, so line current, phase current are same. Now what else needs to be computed? We have computed the line current, that is done. Now the next thing is power factor. Okay, we will calculate the power factor also. It's not a big deal for us now. We can actually use this power triangle also for calculating the power factor. So we can use that only, or if possible we can take another but right now let me use this only. Both are given na. So this angle is your theta na, this angle is theta. So cosine of this is your power factor angle. So we can write simply What is cos theta? Cos theta is base. Base is 10 megawatt divided by hypotenuse. How much is it? It is 10.44. This is also MVA. Now you have to remember that dimensionally MVA and megawatt are same. So let me write this. You should know this. Remember dimensionally, from the point of view of dimension. So that's why I am writing, remember dimensionally megawatt and MVA are same. MVA are same. Although they have different significance, one is denoting the apparent power, another is the active power, but dimensionally they are same. So from this you can easily calculate cos theta equals to how much? It is 10 by 10.44. So let's calculate 10 by 10.44, 10 divided by 10.44. So how much it is coming? 0.9578. So I can approximate it 0.958. So let us approximate 0.958. Now we will cross check this value from another alternative, 0.958. This is we have calculated in some way. Now let us do one thing. Let us now equate these two things of active power. I mean to say that we can compute the value of Vt, no doubt. What is the value of Vt here? Vt is nothing but it is VL divided by root 3, because it is star connection. It is star connected. This thing is star connected or Y connected, whatever you call. So since it is star connected, it will be 11 into 10 to the power 3 divided by root 3. So that will be a Vt. So how much is coming Vt? Let us see. So we have to divide 11 by root 3. Root 3 means 1.732. It is coming like this, and now if you you can write 6.35 kilovolt simply, 6.35 kilovolt. So this is a 6.35 kilovolt, 6.35 kilovolt. That is your Vt. Now remember, we have seen the expression for active power delivered. Let me show you, which I have written earlier. In one case, you can write 3 Vt EF, this thing divided by Xs and then multiplied by sine delta. And another active power is 3 Vt Ia cos theta. So we can equate this. So let us equate this. So one active power expression was definitely 3 Vt into Ia into cos theta. Another is 3 Vt into EF whole divided by Xs multiplied by sine delta. So we know how much is Vt. Vt is your 6.35 kilovolt. That means into 10 to the power 3. Ia is your 548 ampere. Cos theta was your 0.958. Let me check it. So we can check it actually. So 6.35, 0.958 and 548. Okay, fine. Now we need not write in this way. Actually we can see here that 3 Vt and 3 Vt, they are actually cancelling each other. So we can calculate the value of Ia cos theta. But now I would like to just keep this thing in hold. You have understood, maybe you have understood why I am going to keep this thing in hold. Let me tell you why. Let us first calculate the value of EF. So what is EF? So for calculating EF, I will again take you back to this particular diagram which we have drawn earlier. So this is a very simplified but nice way. It will save lot of labor in terms of phasor calculation, the complex algebra and all those things. So this was the diagram which we have drawn earlier, and from here we know what is EF. EF equals to, this thing is your square root of Vt sine theta Vt sine theta plus Ia into xs, this thing we have to add together. So that will be your AC plus AB plus Vt cos theta, that means OC. So this is a Vt cos theta, this thing whole square. So we have to find like this. So let me calculate. So Vt we have known it is your 6.35 kilovolt. So I will calculate in terms of kilovolt. So 6.35. And what is sine theta? We know cos theta is 0.958. So we know that we have calculated. So I will write this thing in a box kind of thing. Calculated earlier. That cos theta equals to 0.958. So from here we have to calculate the value of sine theta. Obviously the value will come very small, but let us see how much it is. 0.958. So we have to find the cos inverse. Sorry, so let me write 0.958 cos inverse of this. So it is coming 16.66. Now I have to take the sine of this. So it is 0.286. You can approximate it to 0.287. So 0.287. So it is your 0.287. 0.287. So let me erase this thing. 0.287. 0.287. This is your sine theta. So now you have to multiply this. Vt is your 6.35. 6.35. So let me write 0.287. That is what I have written. I can show you. 0.287 for sine theta multiplied by Vt, that is your 6.35. But this is in terms of kilovolt. 6.35. So I have multiplied. Now I have to square it. So if I square it, it is coming 3.32. 3.32. So let me write 3.32 here. So I am writing it after squaring it. 3.32. 3.32. But I have done a mistake. I have done a silly mistake. You should notice it. So let me correct myself. I have to not square Vt sine theta alone. I have to square Vt sine theta plus Ia xs. So Ia I have already calculated to be 548 and xs is given as 5 ohm. So 548 into 5. So let me correct myself. It won't be square, so I am taking back the square root. So it is, let me just simply write 0.287 multiplied by 6.35. 6.35. So that is coming as 1.8. 1.82 I can approximate it, 1.82. So let me write that 1.82. So this is your 1.82 plus. So 1.82, that is your Vt sine theta. Vt sine theta. Now what is Ia? Ia is a 548. Xs is your 5 ohm. So 548 into 5 is how much? 2740. But I have expressed this in that thing in kilovolt. Remember, I have written 6.35 for Vt, but that was in kilovolt. So I have to also express this thing in terms of kilovolt. So I will divide this by 1000 to get in kilovolt. So it is coming as 2.74. So I will write that as 2.74. So 1.82 plus 2.74. Now this thing you add and then square. Likewise, what is Vt cos theta? Vt you already know it is 6.35. Cos theta is 0.958. So let us multiply 0.958 multiplied by Vt. Vt is 6.35. So it is giving as how much? 6.08. 6.08. So 6.08 6.08. This thing you have to square. Now if you square them, add them and take the square root, you will definitely get the excitation EMF per phase, that means EF. So EF is your excitation EMF per phase. So let us square them and add them. So 1.82 plus 2.74. 1.82 plus 2.74, 2.74. We have to add them, then we have to square them. So if you square them, it is coming 20.7936, 20.7936, 7936 plus 6.08 square. So 6.08 square, 6.08 square, 39.9664, 36.9, sorry, 36.9664. So we have to add them, 36.9664 and 20.7936. So 20.7936, I have to add 20.7936 is this one. Now I have to take the square root. So I am taking the square root. I am getting 7.6. So EF is coming as 7.6 kilovolt per phase. So this thing is your 7.6 kilovolt. This thing is your 7.6 kilovolt. Now once we have computed EF, now we are in a position to calculate your sine delta. Once you calculate sine delta, you can calculate delta from there, that is the load angle. And power factor already we have calculated. Now you see, in the beginning we have assumed that okay, we will cross check that later. You actually you can verify it later, that for an overexcited alternator, let me write it, for an overexcited alternator, this particular relation stands true. For an overexcited alternator, we can write that EF cos delta will be greater than Vt. So once we know the value of delta, we can verify it. We can verify our assumption which we have done in the beginning, that it is overexcited. So we can verify our assumption later on. We have assumed in the beginning it is overexcited. So now let us calculate the value of delta. So how we are going to calculate the value of delta, I will show you. So before we start, we will again now rewrite this equation once more. We already know, but we will not again really write it. I will just copy it. Let me show over here. So from here we will write the things. So what we can see, what we know actually initially. Let me put that thing inside a box. What is it what we know exactly initially? So what is it? Cos theta is known to us, 0.958. Okay, Vt is going to cancel anyway from both sides. XS, that is synchronous reactance, is your 5 ohm. We have calculated just now EF. EF is your 7.6 kilovolt. Let me check it once more. 7.6 kilovolt EF. Cos theta is known. So now from here we are in a position to calculate sine delta. So we can cancel this 3Vt from this side and this side. So we are left with Ia cos theta equals to EF divided by XS into sine delta. So sine delta is what we want to now calculate. We are interested. We have already calculated EF. XS, that is synchronous reactance, was provided in the problem. Ia we have computed to be 548 ampere. So 548 ampere. Cos theta is 0.958, and EF is your 7.6 into 10 to the power 3 this whole thing divided by 5, this thing multiplied by sine delta. Now by any means the value of sine delta has to be less than 1, that is of course known to all of us. So let us see what is the value coming. 548 into 0.958. So 0.958 into 548 is now again we have to multiply by you can see here now this 5 will go to the left side synchronous, so it will be multiplied by 5, so you have to multiply by 5. So I am multiplying by 5, so this is what is coming. Now you have to divide this thing by 7.6, so you have to divide this by 7.6 into 10 to the power 3, so I can write this as 7600, so you will get this one 0.03655. so that is your delta, which is very small. So let me do one thing. This was your EF was computed by taking 6.35 only, that is the phase voltage, and line current, phase current are same for star connected. So let us see, we are going to take the sine inverse of this, what is coming. So sine inverse, it is coming as 2.094. So let me write that delta is coming as 2.094. now this is very small angle 2.0, and let me compute once more. 3 Vt into Ia cos theta. Now we can do one more thing, is that active power delivered is your 10 megawatt, right? So we can write here 10 megawatt. I am just showing it an alternate way. I need to cross check it. So let me write it here, is that 10 megawatt, that means 10 into 10 to the power 6, 3 Vt into EF divided by XS into sine delta. So on this side you are having the active power 10 megawatt, 10 into 10 to the power 6 watts. Now Vt is your 6.35 into 10 to the power 3, and EF is your 7.6 into 10 to the power 3. EF is your 7.6 into 10 to the power 3 whole divided by XS, that means 5, and this whole thing I have to multiply it by sine delta. So let me bring this thing little bit here. So this thing will be multiplied by sine delta. So let me multiply this by sine delta. So what do you see? 10 to the power 6 thing gets cancelled from both sides, and you have here 10 into 5, that means 50. This whole thing you have to divide by 3 multiplied by 6.35 into 7.6. that thing will be coming as your sine delta. So let us see what is the value of delta coming. So 7.6 into 6.35, 7.6 into 6.35, 6.35, this thing you have to multiply by 3. So this is what is coming. Now if I take the reciprocal and then multiply by 50, which was there in the numerator, 5050, so it is coming 0.345. now if I take the sine inverse of this, the angle is coming as 20.20. so the value of delta will be 20.20. so value of delta is your 20.20. so maybe some silly mistake or calculation might be here the problem, otherwise the thing would have been the same. So if I just find it here, so we can do one thing, we can let's say we are not going to calculate this way. We have been able to calculate that the value of the load angle delta. So that load angle delta is computed. Now from here we will calculate the power factor. Delta is known now. Now we will calculate the power factor from this equation. So let me erase this. So let us calculate the value of the power factor, and we will just cross check it like that only. It will be working like a cross check. We have already calculated earlier what is the power factor, but we will just like to cross check this. So from here only we are getting what we are getting, 3 VT cancelled. So this is your IA into cos theta, and this thing is your EF divided by XS into sin delta, right? So IA is your 548 multiplied by cos theta. EF is your 7.6 into 10 to the power 3 whole divided by 5 into sin delta, sine of 20.20. So from here we can calculate the value of cos theta. Obviously value has to be less than 1 or equal to at most. So 7.6 into 10 to the power 3, that means 7600 divided by, let me write first that sine of this. So sine of this angle is 0.345 into 7600. So we have computed the numerator part. Then we have to derive, you have to divide this thing by denominator, that is 5 into 548. So let us divide this thing by 5 into 548. 5 into 548. So we should get back the value of cos theta. Now it is tallied initial whatever we have calculated earlier. So it is cross check 0.958. So you can write this as 0.958. So this is your 0.958. So this is a cross check thing. Okay, you are basically cross checking it. Okay, so this thing is cross checked. So we have cross checked the value of cos theta. That means your power factor. So we have calculated all the things. We have computed everything. Load angle delta is computed. You can see here. This is your load angle delta. This thing is your load angle. This is your load angle delta. This is your power factor, and this is your excitation voltage, EF. EF was your excitation voltage. So this thing is your excitation voltage. This is also computed. This thing is your excitation voltage. This thing is your excitation voltage. Now remember, I have said that we can cross check this thing whether EF cos delta is greater than VT or not. So let us cross check that, because it will serve as a good example that we have cross checked what we have said in the beginning. So we have to find EF cos delta. So let me write, you have to check whether EF cos delta is greater than VT or not. So let us check it. EF is your how much? 7.6 kilovolt. Cos delta, that means cos of 20.20. And what is VT? 6.35 kilovolt. So I am not writing the kilovolt factor. Now let us see cos 20.20 how much it is. 20.20, you have to take the cosine of that, then you have to multiply by 7.6. How much it is coming? It is coming 7.13. So this thing is coming as 7.13. So this is greater than 6.35 kilovolt, right? So this thing is verified. This particular thing is also verified. This thing is verified. So now we have not made any wrong assumption. We have done the right assumption by assuming that it is overexcited. So if the alternator is overexcited, it will operate at lagging power factor. And how do we check whether it is overexcited? This inequality has to be satisfied. So this is the condition for overexcited alternator. So this is the condition for checking. This is the condition for overexcited alternator. Condition for verifying. You can verify it. Condition for verifying overexcited alternator. Overexcited alternator. Now all the things which have been asked to compute in the problem has been solved. You can see it. We have computed the load angle delta, then we have computed the power factor. Actually we have cross verified it, power factor. We have computed the value of EF, that is the excitation voltage. We have computed the value of line current. So these things are done. So in this way you can solve this problem. So let me end my explanation here. Thank you.